So suppose we want to estimate this sum, the sum from n equals 1 to infinity of 1 over n cubed. We know we can't get that value to be exact, but we can have any desired degree of accuracy that you want, just a matter of how much time are you willing to spend computing it. So let's say we need an accuracy of 1/1000th. How many terms do you think we'll need? This is 1 over n cubed this time, not 1 over n squared. Again, we know this is a convergent series because it's a p series with p greater than 1, and that's something we want to have as part of our vocabulary. So what I want to do is say that I know that the remainder is less than the integral from n to infinity of 1 over x cubed dx. Right? So what I'll do is I just won't say what n is, and I'll just go ahead and do the integral. So that integral is equal to the limit as b approaches infinity of so we know that this antiderivative is going to be, it's x to the negative thirds, right? Should I write that? Okay, fine, I'll write it. It's the limit as n approaches infinity, as b approaches infinity, of the integral from n to b of x to the negative third dx. All right, so that antiderivative, I'm going to raise the exponent 1, get x to the negative 2, divide by the new exponent, so I'm going to have negative x to the negative 2 over 2, and we're evaluating that from n to b. So now both my limits of integration are variables, but one of them is fixed relative to this limit. So only one of these variables is actually the limit variable. So the n I can essentially treat like a constant. All right, so we can also write this as the limit as b approaches infinity. I think it'll be a little bit clearer if I write this negative exponent in the denominator where it belongs. That's negative 1 over 2x squared, right, with the x to the negative 2 in the denominator from n to b. And then so that's going to equal the limit as b approaches infinity of negative 1 over 2b squared, right? That's plugging in the b. And then I'm going to go minus negative, so plus. And when I plug in the n, I don't need the limit because n does not depend on b. So I'm going to have just 1 over 2n squared. And this limit, the denominator expands without bound. The numerator is bounded, so this is equal to 0 plus 1 over 2n squared, which equals 1 over 2n squared. All right, so the nifty thing that I've got now is if I want to bound the error, I know that for n terms, if I add up n terms, that error has to be less than 1 over 2n squared. So if I want the error to be less than 0.001, all I have to do is solve the inequality. 1 over 2n squared is less than 0.001. So that's easy enough to do. I get 1 is less than 0.002 n squared, multiplying both sides by n squared, which I can do because n is positive, because n is a natural number. All right, and then so 1 over 0.002 is less than n squared, so 500 is less than n squared. We like the idea that the n should be larger than something. I need to add up at least so many terms in order to get this much accuracy. Sort of makes sense. So square root of 500 is less than n. And that turns out to be, I did that in my calculator ahead of time, it's about 22.36. But there is no a sub 22.36. I can't add up 22.36 terms. So what I do is I say use n greater than or equal to 23. And then I will have that degree of accuracy. Yeah. All right. So, and then, you know, what that tells me is that I know, here, let's see what that tells me over here. So I know that if I do the sum from n equals 1 to 23 of 1 over n cubed, all right, what do I get when I do that? As you realize I did that incorrectly and when I did it ahead of time, as often happens. So let's see. Math 0 gives me a sum 0. Thank you. We're going to do the sum from, we have to use x here. X equals 1, 2. We're going to go up to 23 of 1 over x cubed. All right, and I get 1.20115. 1.20115. All right, and I know that my accuracy is within 0.001. So this is what's a good way to say that? That the true sum is more than 1.20115. All right, but since the accuracy, right, we've already bounded the error. The error is less than 0.001. Our error is less than 0.001. If I could put it this way. The error is less than 0.001 for n terms. All right, so our error is less than 0.001. So that means the S is less than 1.20215. But we don't. Yeah, I mean, well, I guess we could say that. So now, here's what we know about the sum. This is the the true infinite sum, the sum from n equals 1 to infinity of 1 over n cubed. All right, so we actually have a pretty good handle on it. It's between 1.20215. Whoops, if I can write that. It's between 1.20215 and 1.20115. That sum is between those two values. So I have it within 0.001 accuracy. All right, so that's fun, but we actually can even do better than that. So we can actually get closer to this sum by realizing that not only is there a maximum error bound, there's also a minimum error bound, which will cause us to go back and look at our Riemann sum again, which is what we will do next.